This afternoon, I'm just going to talk a little bit about some of the work we've done at RETEC with regard to some of the advances in the processes for production of gamma titanium aluminide bars as well as powder. So this is really a culmination of the last many years, quite a few years worth of work that we're presenting here as a summary and sort of an overview. For those of you who are not familiar with RETEC, we are located in Northern California. We're about 200 kilometers north of San Francisco, right on the main highway. And we're very blessed to be in a very beautiful area of California with a lot of vineyards around us, and to the north, redwood trees, and to the west, maybe an hour or so drive away is the Pacific Ocean. So we feel pretty blessed. And anyway, just to let you know where we are, we're in Northern California. Okay, RETEC is an engineering and manufacturing company. We do a lot of custom equipment development and melting. We have our own research and development department, of which I am the head. We have a plasma arc melting system capable of up to 1,200 kilowatts. We have inside the same chamber there shown on your left is a cold wall induction crucible capability for up to 600 kilowatts and 45 kilogram titanium capacity. Recently, in conjunction with a number of very generous vendors, we have put in together in what we call our R&D E-beam system. Features von Ardena guns and technology for beam guidance technology. That is a 300 kilowatt two-gun system that we have in our R&D department, and that's been operational now for about 2 years. So getting back to the motivation for the titanium aluminides, for those of you who are familiar, this probably is just going to be if you will, a reset. But for those of you who are not completely familiar with the titanium aluminides, what's driving this, as we heard this morning in some of the talks, is, of course, fuel efficiency, not only in the aerospace industry, but there's also some interest here in Europe, as well as in the United States, with regard to automotive turbochargers. And that was the main driver for us to develop what we call our gamma PAM concept that I'll talk about later. So the idea is to replace nickel-based superalloys with titanium alloys for the lighter weight. We're looking at, actually, as Professor Alexandrov talked about just a little bit as well, the newer, higher performance titanium alloys, the gamma titanium aluminides. So when we say new, though, we're talking about GE. When I was in graduate school in the late 1980s, we were working on them back then. So these things have been around for 25 years, but yet, as many of you in the metal cycles and in the metals business, sometimes that still can be considered a new alloy. What we've been doing is at RETEC, we've been collaborating with other companies to try and bring this technology for certain applications to market faster. We see a lot of benefits working with two companies rather than just all by ourselves. We get a little different market approach, and we can leverage some of our melting technologies for our partner and or our customer. So we introduced the gamma PAM and also what we call a gamma VIM. I'm not going to talk about that today, at the Therm Process conference in Dusseldorf back in 2015. So we're in the middle of bringing this to market and letting many of our potential customers know what we can and cannot do with this type of technology. So in the end, as again was briefly touched on this morning, especially in the automotive market applications, it truly does come down to it's all about cost. So please bear that in mind. What we've done and what I present here is kind of an assessment of the various melting technologies as it relates to titanium aluminide. And we have just three main guidelines here, or criteria: how well you can keep the alloy element retained in the melting, the ability to mix the material, as well as projected, these aren't exact, but projected operating costs. And we looked at vacuum arc remelt, electron beam, cold wall induction, or some people will say induction skull melting, plasma arc melting, and some of what we call the newer techniques, induction levitation. So with regard to alloying retention, as you see here, we kind of rated each one. And the vacuum arc remelt is somewhat complicated for aluminum. Electron beam, of course, also complicated for aluminum due to the high vapor pressure, or relatively high vapor pressure for aluminum. cold wall induction melting actually can be quite effective for melting the titanium aluminides, because in many cases you can backfill the chamber and melt at atmospheric pressure. The same goes for plasma arc melting. You can actually melt at atmospheric pressure and lower the aluminum loss. Same assessment, excellent for induction levitation. With regard to mixing, as Mr. Alexandrov mentioned, that sometimes in VAR melting you actually have to melt quite a few times in order to get it to mix. So we rated that as fair. Electron beam melting tends to be the similar argument could be made. It could be fair, it could be poor, but it doesn't have the ability to actually motor the molten metal compared to some of the other processes. Cold wall induction, excellent induction melting due to the stirring, and provided, of course, you have the correct skull management techniques and melt practice. Plasma arc melting, very good also for mixing, and induction levitation is an excellent means of mixing. Operating costs we would anticipate for vacuum arc remelting, though, would be low. It's very well known, very simple, very easy to maintain and operate. Electron beam, we would rate that as medium. Cold wall induction, of course, due to its very low thermal efficiencies, its operating costs are high. Plasma arc is also a medium. We rate it as medium. And the induction levitation, it's still somewhat if you will, in development. No one's really doing this in production. So we anticipated high operating costs for that. So overall, we kind of combined all these factors evenly and just gave them an even weighted. So vacuum arc remelting, we would give a fair rating. Electron beam melting for the titanium aluminides, probably not the technology of choice. Cold wall induction melting, very good. Plasma arc melting, anticipated to be very good. And the induction levitation melting, only because there's some still unknowns about the exact quantities of how much you could levitate at one time. We rated that somewhere in the fair to poor category. So what we took a look at and what we've been kind of developing over the years was this idea that can we match and marry cold wall induction with plasma arc melting and bring that to market. So what we've been looking at, again, over the past 5 years is primarily ingots, and then lately it's been an emphasis on powders. But we looked at a hybrid system using plasma arc and cold wall induction together. We are also looking at ways to improve the thermal and primarily the electrical efficiency of cold wall induction. We've been looking at castings with regards to that aspect. That has to be fast cycle, and there has to be a design focus to, if you will, keep the capital expenditure low and a very high degree of automation. We're going to focus not so much on castings, but the ingot and powder. In the future, we see just a continued use of these teaming partners to bring it to market faster. And with regard to powder, there's going to be some breakthrough with regard to, if you will, we're looking at induction melting, drip gas atomization, as well as some sort of non-contact nozzle gas atomization. I'll touch on those a little bit more later here in this presentation. But those are just the main product areas that we've been looking at. So as I mentioned, Gamma PAM, it's a hybrid system between plasma arc and induction melting. This system, the main melting chamber is in the center. Off to the left is one of the feeding systems where the briquettes are loaded into the vertical towers shown on the left. And this system, the customer specifically wanted the ability to remelt powder. So on the right is a rotary feeder with a vibratory mechanism that will then feed the powder directly into the ingot withdrawal mold. So schematically, the Gamma PAM looks more like, if you will, the system shown in the cross section here. And just as a side note, our partners in this development is Hanseatische of Handels, excuse me, or Titanium Solutions. They're located in Bremen, Germany. We've been working them. It's been a very good working relationship with those folks to bring this technology to market faster. The state of the system now is that we do have a patent on the actual plasma arc melting based system. All of the melting occurs inside water-cooled copper vessels, and we've demonstrated the melting capabilities at the 50 millimeter diameter scale ingots, 100 millimeter and 250 millimeter diameter molds. Those are existing molds that we have now, we've demonstrated. There are other size molds that could be made if necessary and if desired. And again, everything's water cooled inside of a vacuum sealed melting chamber, and melting occurs at atmospheric pressure to retain the aluminum in the material. So just an idea of the cold wall induction crucible. I'm going to talk a little bit more about this. Shown an actual crucible shown on the left. It's an actual assembly specifically designed to be plasma melted and poured into, and it's kind of more diagrammatically shown here on the right, and plasma melting system to pour into on the upper right hand side. So a little more detail here. What we've been working with was Fluxtrol to enhance the electrical efficiency of the mold, the ingot withdrawal mold. And we've been working in the areas of coil design and also, but most importantly, the application of what are called soft magnetic composite materials. This is a product that Fluxtrol makes on a daily basis. That's their line of business. And we've applied that to the cold wall induction mold itself. So we've looked also at the optimizing the coil design as well as the implementation of these soft magnetic composites with regard to their size as well as their locations within the mold. And so far we've seen electrical efficiency improvements of at least 30%, which is a big deal for cold wall induction melting. And in some cases, the actual melting improvements, not in all, but in some cases, melting improvements of up to 50%. And we melt 50% faster is what we mean by that. So just shown here on the right is just a basic diagram of how we modeled the system at Fluxtrol and took the results and applied them to practice. So just some of the results here shown on the, just a brief picture comment of this is since we have a little bit of time, the mold is shown on the left, the induction melting. On the top of the mold off to the left-hand side is a piece of splash material that came from the hearth. And as you can tell here, there's minimal influence of that material on the melting performance within the mold. The surface finish of a typical ingot is shown here on the right. The ingot is actually laid on top of a table, and I took the picture so to give it a perspective. So if it looks kind of funny, it's because the picture is actually cocked off 90 degrees from how it was originally taken. But to give you an idea, here's a table of results for various 53 millimeter diameter ingots that we've made. TNM shown on the very left. That's a titanium niobium aluminide composition, molybdenum composition, where the niobium is right around 9%, and the boron is 300 parts per million. Aluminum is 28.7. We're showing pretty good. I'm very pleased with the chemical results on this. We've also done what's called a beta titanium alloy for a customer here in Europe, looking at a medical application. And in this case, they were specifically asking us to introduce oxygen as titanium dioxide into the melt. And they were quite pleased with our chemical analysis results there. We've also done some work with 6242 with boron additions and at different levels of 1% boron and 0.5% boron. And that was quite a challenge, but also we've been able to do it. So the idea here is that we have mixing not only in the hearth but in the mold, and that's what we feel is very important in the success. So what we're doing here is we're taking on composition compacts to start with and converting them in one melting operation to on composition final alloy ingots. So that's one of the ways that we see that we can reduce the cost of the production of the titanium aluminide materials is by only melting one time. It's also a quality control advantage potential there as well. Some of the other work that we've done, as I mentioned, with regard to the titanium aluminides has been in the area of specifically gas atomization of powders. The traditional approach that we've been offering for many years and now are able to actually offer as an equipment supplier because of the patent expiration is the cold wall induction melt, what we're calling the TIGA. We've looked at evaluating different nozzle materials for that type of a system, where it's yttria, graphite, or even coated graphite for the titanium aluminides, as well as we've introduced what we call our RIGA system, which is induction melt and electrode drip. And we're planning to build an actual demonstration system. We're in the process of doing that right now. and that will be operational sometime later this year. We're projecting that to be operational at our facility in Ukiah in October. And the primary focus there will be for looking to develop process optimization for not only the titanium aluminides, but other titanium alloys for powders. So just some diagrams here to give you a feel for what we mean by TIGA. It's a cold wall induction melt bottom pour gas atomization process. It's a clean melting, if you will, in a cold wall induction crucible. As many of you may be familiar with that, typical charge sizes range anywhere from 40 to 50 kilograms for titanium. We can melt and atomize in less than 60 minutes. And then there's an approximate 30-minute or so turnaround time for the system. And the ability for this system is primarily its ability to melt a wide variety of feedstocks. Some of the powder data is shown here in the lower right-hand side. The powder for 6.4 tends to be somewhat coarse. The powder for 48.22 can be somewhat finer, and depending on how you look at your yields, what we've just put is the minus 250 fraction, the yields, and then the resulting flow rates for the powder. But shown on the left, I don't have a pointer here, the atomization tower and the melt chamber are shown on the left with the cold wall induction crucible essentially in the middle of the system. The molten metal comes out of the bottom of the cold wall induction crucible and into the gas atomization die, which is situated at the top of the atomization tower. It's very common. And this system is shown schematically in the upper left-hand corner. There's a small feeding system in the case that some small alloy additions would we desire to be made to the system. So that's what we call our TIGA system. It's cold wall induction melting bottom pouring. Just a few pictures here of the actual components, the tower and the melt chamber in the middle, the cold wall induction crucible over on the left, bottom pour, it's sitting on top of the tower inside the chamber, and an actual atomization conditions shown over on the right. The other system that we're developing actively right now, as I mentioned, we'll have this up and operational later this year, is what we call a Riga. That's a rotating electrode, a very slowly rotating electrode for those of you who are not familiar with this process. Very similar to the ALD-IGA process. It is completely crucible free. We are looking at the 2-inch or 50 millimeter and the 4-inch or 100 millimeter diameter configurations to melt charges up to 35 kilogram maximum. And the atomization time, melt and atomization time, will be also less than 60 minutes. This process is typically known to produce finer powder, and our data also confirms that it can produce a finer powder. So our D50 of the minus 250 fraction, we certainly are going to guarantee 100 microns. And the powder yield is a minimum of that size fraction, a minimum of 70%. Depending on if it's an additive manufacturing process or a metal injection molding process, the end customer then starts looking at the degree of very fine powder that can be produced in the process. But right now what we're saying is that we'll, for a yield of the plus 10 micron to minus 70 micron, we'll guarantee a minimum of 20% yield for that size fraction within the minus 250 fraction range. And again, the flow rate of the powder is actually quite good for the additive or bed manufacturing processes. Okay, so just a very simple pictures of the Riga system shown on the left, the decking, and the melt chamber is actually quite small. Most of the system is actually the feeder mechanism for the electrode. These are about 1 meter long electrodes that are fed into the system, and a actual melting and atomization conditions shown on the right. So you see how the dripping action of the induction coil melts the material. We're also looking at other areas and other ways to produce powder via what we call a non-contact nozzle. We did some proof of concept tests last year and completed those in 2016. And we made spherical powder out of a gamma titanium aluminide composition shown on the right. The actual composition was TNM. And our process design goals were we wanted a semi-continuous operation with low production costs. And we wanted to be able to take raw material and convert it directly to powder. And we wanted the system to have potentially the ability to recycle the oversized powder directly in the process. And of course, the ultimate goal will be to optimize the powder yield of the finer powder. So what we've been working with is a plasma arc melting technique, and we're in the process of setting this also up at our facility in Ukiah, which will be ceramic free and semi-continuous, because we can take the feed material and feed it directly into a tilting hearth shown in the center of the system and melt with plasma arc. We'll then tilt out of the plasma arc and atomize accordingly. There will be no consumables in this other than the feed material, of course, in this process, and we think this may have a high throughput potential. We have preliminary promising results, but we're under development within our R&D department right now. So hopefully within the next year or so, we'll have some actual results from this approach. But the idea is to take raw material in one step, convert it into the powder, similar to the TIGA process. That again takes raw material and converts it into powder, but it's with induction melting, which has some throughput limitations with regard to the nozzle design and nozzle life. Okay, so just a brief pictures of the proof of plasma arc cold hearth atomization concept. Shown on the left is the plasma arc melting and tilt pouring of the material, and shown on the right is a picture of some spherical powder that we produced last year. This is a scale down in the right-hand corner, shows a 60 micron scale, so the particle shown in the center is roughly about a 75 micron particle, again gamma titanium aluminide. So we're anticipating having this system ready about August of this year for our own internal testing, and then later customer testing and evaluation for any interested parties late in the year and early into 2018. So I'll just wrap up with some conclusions here. Our gamma PAM system, we call it the PAM size, but officially we're labeling it. We have this system at RETEC, and it has aided with in a couple of areas. Of course, equipment sales, which is our primary business, material evaluation, again working with our customer and partners, in this case Haun in Bremen, Germany, both for composition and microstructural evaluation. We can also, because it's a pilot scale type system, we can develop economic models, and we have done that, and project actual costs. The validation of our cold wall induction crucible design was also enabled by that system. And again, we've seen, as I mentioned, a 30 to 50% improvement in the cold wall induction melting performance and electrical efficiency. In 2017, RETEC is investing heavily in these R&D atomization systems. We're going to look at converting for the Riga system, process optimization work, and then for the newer complex titanium alloys, direct conversion of compacts to powder in the PAM system. And we're primarily looking at those alloys that are difficult to cast into ingot. So where there's an intermediate form in the Riga system or the IGA system, you always need that intermediate electrode form, which can potentially add costs. Not in all cases, but it can potentially add costs. And sometimes some of the alloys are not even amenable to making the ingot or the electrode in the first place. So you have to have a different technique. So, and those alloys that are susceptible to nozzle erosion, that's one of the other thing that we're kind of trying to focus on, is some sort of non-contact way to create the powder. And ultimately, the customer evaluation that these systems will give us prior to purchasing, we think that's a main advantage to our approach. So with that ends my talk. If any of you have any questions, I'd be happy to handle them take them at this time. Yes. Primarily it will be industrial sizes. The two systems that will be providing up to about 25 kilos of powder. 25 kilos. So it won't be huge quantities, but it will be significantly large enough that, if you will, if we wanted to make multiple batches and then have that added into a bed powder additive manufacturing, you could do that. So most of those systems take somewhere around 50 kilos, 30 to 50 kilos, in that range, depending on the manufacturer, to actually make some parts. Yeah. Mhm.
The chemical composition of the powder, you're examining separately, or it is the composition of the consumable electrode?
Both. In the consumable electrode, there's virtually no change at all. The only issue is, if you will, the process control, as you mentioned in your paper, with regard to oxygen. So we do have to watch the rate of rise or the leak rate in the chamber. But essentially for that process, as well as for the TIGA process, there's virtually no change in the composition of the, from the starting to the, to the powder. Yes. Now, when we look at converting directly from the raw material to the powder, what we have is in the raw material is the exact composition, very similar to what you did in your VAR melting. We make those compacts or briquettes, the exact composition needed for the, and that's very common in all of our plasma arc and electron beam melting systems that we make. It's very common for the customers to do that.